Hello learners, I am Dr. R.B. Malati, Assistant Professor at Chhattisgarh Swami Vivekanand Technical University, Bhilai. I welcome you all again to the course Essentials of Surveying Application and Techniques. Today we are going to explore photogrammetry. We can say it is an emerging field that has huge career opportunity for people who are really interested in it. In this module, we will be speaking about the definition of photogrammetry, photogrammetry process, types of photogrammetry in which we look into terrestrial photogrammetry, geometric process of terrestrial photogrammetry and some example problems associated with it. So, what is photogrammetry? In simple terms, it is about merging photograph with geometry to measure and analyze the physical world that we are in. Let me ask, how many of you have taken a panoramic photo with your smartphone? Most of you. It means everyone is already into some basic level of photogrammetry. So, if you see the origin of this word photogrammetry, it comes from three Greek words, photos meaning light, gramma meaning to draw and metron meaning to measure. This photogrammetry essentially means measuring things using light and images. So, why images? For this reason, let's understand the difference between photograph and images. Imagine using a film camera. When you take a photo, what happens is light enters the camera through the lens and hits the film. And what is this film? It is a special material called polyester acetate. Okay, this film further undergoes a chemical processing and negatives are developed, which are then used to make positive prints on paper called photographs. I will repeat, light enters the camera through the lens and hits the film, and this film further undergoes chemical processing and negatives are developed, and from which positive prints are created on paper called photographs. Right. In contrast, when you have a digital camera, light hits on digital sensor instead on a film. This interaction releases photons, generating an electrical current that is converted into voltage and then into digital numbers, which can be easily stored, edited and also shared. So, photographs are physical prints made from film and there is no flexibility of changing it again, and digital images are stored as data and they offer more flexibility. Right. So, that is the idea about image and photograph. This is an era of digital sensors. So, that is why we should use the term image. Let us now start with the early stages of photogrammetry. When we trace its evolution from the Renaissance to the digital age, there are four main cycles, that is plane table photogrammetry, analog photogrammetry, analytical photogrammetry and digital photogrammetry. So, the first practical photo is credited to Émile Lazard in the 19th century. He demonstrated how balloons can be used for taking photographs. These photographs were then interpreted on plane tables for topographic mapping. So, what is topographic mapping? They are nothing but the map that you use in your adventurous hiking or finding a specific location during your road trip. Hope everyone would have used this. And what it shows? The elevation and shape of the land using contour lines, isn't it? Now, back to balloon photography. True, balloon photography was innovative, but it had its own limitation, quite obvious. So, getting into the 20th century, the second stage of photogrammetry flourished. This is analog photogrammetry, where some kind of mechanical instruments were used to create the 3D from the photographs, and it is also obsolete now. Then comes the third stage, where photogrammeters shifted to analytical photogrammetry. Here they scanned photographs in the form of images and they are supplied to the computer, and by using the scanned images we started doing the development. Yes, today we are in the era where we have reached its apex of evolution, and with digital computers the appetite for the digital data is almost insatiable, isn't it? To summarize between what we learned till now is, we understood the definition of photogrammetry, the difference between photograph and image, and we also trace the history of photogrammetry from its earlier foundation in the Renaissance to the sophisticated digital techniques used today. I hope by now you have caught a glimpse of what photogrammetry is all about. Now moving to the next topic, that is photogrammetric process. Imagine you want to make a detailed map of your college campus. First, what will you do? Yes, you will plan your project, deciding which areas to cover and select the right camera that serves the purpose, isn't it? Next, you will make numerous overlapping pictures, ensuring every part of the campus is captured from different angles. Of course, as you are so smart, you will work to enhance accuracy, and for which you place markers in your known locations. Then, once you have all the images, you mash them up, identifying common features by overlapping the photos. And using some software, these mashed images are transformed into a detailed 3D model of your campus. You can then point out exact location, identify features, whether buildings are and the roads are, and analyze this data to bring necessary changes if needed. Finally, you will present your findings through maps or detailed reports. I hope by now you have caught a glimpse of what photogrammetry is all about. Moving to the next topic, that is photogrammetric process. Imagine you want to make a detailed map of your college campus. First, what will you do? You will plan your project, deciding which areas to cover and select the right cameras that serves the purpose, isn't it? Next, you will take numerous overlapping pictures, ensuring every part of the campus is captured from different angles. And of course, as you are so smart, you will work to enhance accuracy, and for which you will place markers in known locations. And then once you have all the images, you mash them up, identifying common features by overlapping those photos. Then you use some software that for matching the images and transform it into a detailed 3D model of your campus. You can then point out exact locations, identify features where the buildings are and the roads are, and analyze this data to bring necessary changes if needed. Finally, you will present your findings through maps or detailed report. So this is the process in photogrammetry. Hope you could visualize. Let us put this visualization into simple steps now. Plan your project. What you do, decide what you want to achieve, where you want to look, and choose the right equipments. 2. Take pictures. Use cameras or other tools to capture images from above or on the ground. And what you make sure? Yes, you will make sure to get enough overlapping coverages. Next, set up ground points. This is place markers on the ground with no location to help your maps are correctly accurate. Next, map up your images. Here you line up your pictures and find the same features in the overlapping ones. Then make a 3D model. This is using a special techniques. You turn your images into 3D model of the ground. 6. Find points in 3D. Yes, here you will figure out the exact position of points on the ground or object. Then 7. Pick out features. Absolutely, you will identify and mark specific things in your pictures like buildings or roads. Then analyze your data. Here you study the information you have gathered to measure things or spot any changes. Finally, report your findings. You will write down what you have learned and share it with others using maps, reports or models. Done. So, to perform such tasks, there has to be some techniques of photogrammetry. The two types are terrestrial, which uses ground-based camera, and aerial, which employs drones or planes to capture images from above. Let me work only with these two symbol bifurcation to make you understand the concept quite clearly. So, starting with the terrestrial photogrammetry. Say now, how many of you have used a camera on a tripod? Few, great either. So, the terrestrial photogrammetry involves taking photographs with camera that can be handheld, mounted on tripod or even suspended from mounts. Then there are two main types of terrestrial cameras used in the photogrammetry. First, we have phototheodolite. This is nothing but the one used by the surveyor to capture detailed image and angles of the land. Next, we have stereometric cameras. These systems use two identical metric cameras mounted at the ends of the camera for capturing two slightly different views of the same object. It is like having two eyes to give you the depth perception. With this background, let us explore more on phototheodolite now. First, let us understand the important component of phototheodolite, for which let us take the Bridge-Lee phototheodolite. Talking little history, John Bridge-Lee, a scientist and a lawyer from London, developed this instrument in the late 19th century. He filed patents in 1894 and by 1896 he licensed the company L. Kasla to produce and sell it. Quite interesting, right? And this Bridge-Lee phototheodolite has got several important components. First, there is a photogrammetric camera housed in an aluminum box with a compass card for orientation. Below the camera, there is a horizontal circle made in 30 minutes interval for measuring angles readable with a vernier scale. And above the camera, there is a telescope and a vertical arc allowing vertical movement and measuring angles up to 90 degrees, also marked in 30 minutes interval. The entire instrument is mounted on a tri-brush base, ensuring stability and level positioning during use. Okay, now a quiz for you. The deal is, in terrestrial method, both plotting, recording are done simultaneously. Say false or true. Yes, the answer is A, and the reason is, though both terrestrial and plane table surveying indicate the same principle, but in plane table both plotting and recording is done in the field, where in terrestrial photogrammetry it involves the same work but done at various places. This is a major difference between the two processes. Now, you visualize that you are taking a photograph from this camera, for which some geometric properties of the terrestrial photographs should be taught to you. First, the camera axis. See closely the figure. Camera axis, as you could see here, is a line passing through the center of the camera lens, perpendicular both to the camera plate, which is negative, and the picture plane, that is a photograph. Next, picture plane. Picture plane is the plane perpendicular to the camera axis at the focal length distance f on front of the lens. Next, principal point. Principal point, which is denoted as K or K dash, is defined by the intersection of the camera axis with either the picture plane, which is positive, or the camera plate, which is negative. Next, the focal length. The focal length f is a perpendicular distance from the center of the camera lens to either the picture plane or the camera plate. Then the focal plane, which is called image plane. Focal plane is a plane perpendicular to the axis of the lens, in which images of points of the object space are focused onto the lens. Next, the principal distance. When the contact points from the original negatives are enlarged before their use in the compilation of the subsequent map, the value of the focal length f of the camera is not applicable for the revised prints. The changed value of f holding the same geometrical relations is known as the principal distance. Next, principal plane, which is denoted as KK dash. It consists of principal line and the camera axis. It is perpendicular to the picture plane and the camera plate. Fiducial mark. A fiducial mark is 1 or 2, even 3 or 4 marks located in contact with the photogrammetric emulsion in a camera image plane to provide the reference. Next, fiducial axis. The two pairs of opposite fiducial marks define two reference lines that intersect at 90 degrees. These two lines are referred as x and y axis or fiducial axis. And finally, we have film base. Everyone know film base is a thin, flexible, transparent sheet of cellulose nitrate, cellulose acetate or similar material which is coated with a light sensitive emulsion and used for taking photographs. There we end the components. And these definitions can be found in any surveying book available in your college library, but you have to take an effort to pick up a book from the library absolutely at your free time. Yes, now again, imagine you are out in the college campus taking pictures of a vertical cliff. Camera is positioned at the specific spot called the exposure station. Having understood the various geometric properties involved, the next step is determining the scale of a photo. This is an important aspect we will focus on learning next. I have to underline Mr. Pankaj covered the scale under the heading Scale, Introduction and its Types in a second lecture, and I believe everyone is well acquainted with it. I will still provide an outline here. So, when we take a photograph of a vertical cliff denoted as AB using a camera positioned at an exposure station O, we need to consider few key elements. The focal length f of the camera, which is the distance d from the camera to the object, and next the actual distance between the points on the object x and the corresponding distance on the image small x. The scale of the photo is like a magic ratio that helps you figure that out. The scale of the photo can be defined as the ratio of the photo distance to the ground distance, and we express mathematically as scale is equal to small x by capital X. Now, why does this work? It is all about the similar triangles. Remember those, they have couple of key properties. The corresponding angles are equal, the ratio of the corresponding sides are equal. So, if you have a small triangle in your photo and a big triangle in your real life, the angles are the same and the sides are proportional, as simple as this. This is why scale is equal to small x by capital X, and it is a magic ratio. Using these properties, you can easily jump between the photo and the real world. And there you have it. Scale is equal to small f by capital D, and this implies small f by capital D is equal to small x by capital X. So, to determine the scale of a horizontal photograph, we need to know the focal length of the camera f and the distance from the camera to the object capital D, right? And now, let us look at how accurately we can determine the focal length f, which is also important for our calculation. Imagine we have 2 points A and B on the photograph, and we measure the horizontal angle between them AOB as theta using a theodolite. By exposing the plate to show points A and B and using the coordinate XA, XB, we can calculate the focal length using the formula f is equal to xa plus xb by 2 tan theta plus root of xa plus xb the whole square by 4 tan square theta plus xa xb. Here is a derivation. Tan alpha a is equal to xa by f and tan alpha b is equal to xb by f. Now, tan theta is equal to tan alpha a plus alpha b, which is equal to tan alpha a plus tan alpha b by 1 minus tan alpha a tan alpha b. As we know the value of tan alpha a and tan alpha b, we can simply substitute on this equation. So, we obtain xa by f plus xb by f by 1 minus xa by f into xb by f, which comes out to be xa plus xb by f into f square by f square minus xa xb. From this, we can get tan theta into f square minus xa xb is equal to f of xa plus xb, from which we can arrive f squared minus xa xb is equal to f of xa plus xb by tan theta. Rearranging, we will get f squared minus f of xa plus xb by tan theta minus xa xb is equal to 0. If we see closely, it is nothing but a quadratic equation, and you all know what formula you need to apply to find the unknowns. So, hence solving the quadratic equation, you will get f is equal to xa plus xb by tan theta plus root of xa plus xb the whole square by tan square theta plus 4 xa xb by 2. Rewriting, we will get f is equal to xa plus xb by 2 tan theta plus root of xa plus xb the whole square by 4 tan square theta plus xa xb. Thus, the value of f can be easily calculated. Let us walk through few basic examples to make this clearer. Problem 1 is on determining the scale of a photograph, and the problem goes like this. You have a photograph of a building taken from a known distance. The distance between 2 points in the photograph is 10 cm. The actual ground distance between these 2 points is 50 meter. Determine the scale of the photograph. And the solution is, we know what is scale. Scale is equal to photo distance by ground distance. Substituting the values given in the question, we get scale is equal to 10 cm by 50 meter. Convert the ground distance to the same unit, that is to centimeter. Hence 50 meter will be 5000 centimeter. Now we can calculate the scale. Scale is equal to 10 centimeter by 5000 centimeter, which gives 1 by 500. So the scale of the photograph is 1:500. Next, another problem on calculating the ground distance from the photo distance. The problem goes like this. A photograph has a scale of 1:1000. On the photograph, the distance between the 2 points is measured as 8 cm. And what is it on the actual ground? So the solution is, scale is equal to photo distance by the ground distance. We are given with the scale. So 1:1000 is equal to 8 cm by x. So cross multiplying, we get x is equal to 8 cm into 1000, which gives 8000 centimeter. Now converting it into meters, x is equal to 80 meter. So the actual ground distance is 80 meter here. Moving to another simple problem, that is finding the height of an object. The problem goes like this. You have a photograph taken from a camera, height of 1.5 meter. The scale of the photograph is 1:200. On the photograph, the height of the building is 7.5 centimeter. Determine the actual height of the building. The solution is, scale is equal to photo distance by ground distance. Scale is given. So 1:200 is equal to photo distance 7.5 centimeter by capital X, and cross multiplying, we get x is equal to 7.5 centimeter into 200. So x is equal to 1500 centimeter, and converting to meter, we get x is equal to 15 meter. So the actual distance of the building is 15 meter. Problem 4, that is determining photo distance from the ground distance. A scale of 1:800 is used for a photograph. The actual ground distance between two landmarks is 320 meter. What should be the distance between these two landmarks on the photograph? That is the question. So the solution is the same. Scale is equal to photo distance by ground distance. Scale is 1:800. The small distance x by 320 meter. Converting the ground distance to centimeter, we get 320 meter is equal to 32,000 centimeter. Now cross multiplying to solve for x, we get x is equal to 32,000 centimeter by 800, we get 40 centimeter. So the distance between the landmarks on the photograph should be 40 centimeter. Hope these problems should give a good idea of how to handle the typical terrestrial photograph scenarios. Now moving to a very good book example. The problem is on determining the focal length of the lens. Imagine you have a photograph with 2 points on it. These points are distance from the principal line, which is like the center line of the picture. One point is 75 mm to the left and the other is 65 mm to the right. Now the angle between these 2 points measured using a transit, which is basically the plane perpendicular to the photo, is 45 degree. What we need to find is the focal length of the lens that took this photograph. So, solution goes like this. The distance of the first point from the principal line x is 75 mm given in the question. Distance of the second point from the principal line xb is equal to 65 mm given. Angle between the 2 points theta is 45 degree. Focal length can be determined from the expression f is equal to xa plus xb by 2 tan theta plus root of xa plus xb the whole square by 4 tan square theta plus xa xb. Substituting these values, f is equal to 75 plus 65 by 2 tan 45 degree plus root of 75 plus 65 the whole square by 4 tan square 45 degree plus 75 into 65, which comes around to 169.02 mm. Therefore, the focal length of the lens is approximately 169.02 mm. Done. Here is another example for you to solve by yourself. The distance from 2 points on a photographic point to the principal line are 68.24 mm to left and 58.48 mm to the right. The angle between the 2 points measured with the transit theodolite is 44 degree 30 minutes. What is the focal length? Identify and give me the answer in the comment box. Check whether you are getting 154.7 mm. I assume your concepts are clear now. By understanding these concepts, what is achieved? Yes, you can easily and accurately determine the scale of the photographs in terrestrial photogrammetry, which is an important application like creating detailed maps and studying geographical formation. So, there we have it. To summarize, what we learned till now is we understood the definition of photogrammetry, the difference between photograph and image. We also trace the history of photogrammetry from its early foundation in the Renaissance to the sophisticated digital techniques used today. We have also learned how to determine the scale of terrestrial photographs and its focal length, and that ends the terrestrial photogrammetry. So, in the next class, we will discuss on aerial photogrammetry and others. Thanks for your attention. Happy learning.